Hello people, this is a follow-up video to the one that I already prepared, and it has to do with finding the natural frequencies of a single degree of freedom system, a mass spring damper system. Uh, Except that in the first video, I collapsed everything to one point. Here in this video, I would actually like to create 2 points and literally point a spring between these two support points, okay? As far as the calculation goes, it makes no difference, but I personally like to see my spring and the mass instead of seeing everything collapse to one location. Now, I would like to refer to solving this problem as killing a fly with a cannon because obviously the answer is going to be square root of k over m. However, if things worked out, and this is going to be modeled in a sophisticated tool, basically the finite element package within the 3D Experience release 2023X, which incidentally is the Abacus program. So these videos are intended for people who would like to or are novice to 3D experience or who are perhaps familiar and experienced in Abacus CAE program and they want to see what are the changes when it goes from the Abacus CAE to the 3D experience. And there are some differences as far as although it's the same solver, but there's some functionalities are different, some are not completely integrated within the program. But anyway, let's move on. It's a very simple problem, mass spring damper system, and this problem is actually taken from a YouTube channel right here, where the person, this professor, is modeling it entirely in the Abacus CAE program. So this is going to be actually a good observation on what are the differences between how it's done in CAE, Abacus CAE, and how it's done in 3D Experience. Now, obviously, these are standard third-year vibrations course formulas. So now, if we want to get the natural frequency, all we need to do is the frequency step. But if you want to get the damped natural frequency also out of the program, after you do the frequency step, you do a complex frequency step, and it's going to spit out this number for you. So let's go ahead and do that. Let's see. Yep. So I'm going to create 2 points. One of them is going to be Z at location 0, 0, 0, and that's going to be the support. And there's another location, and the distance of it is really irrelevant, maybe 60 millimeters to the right, and it's going to be, or let me make it 20 millimeters to the right. It's going to be the location where the mass is going to come. So I'm going to create 2 points. One of them is at the origin, and then another one 20 millimeters away. And on purpose, I'm going to do it along the y-axis. You will see that there are some issues that you have to pay attention to when you do this. So okay, there we are. So there's 2 points here. One is over there, and the other one over here. Okay, this is as far as the geometry is concerned. Now we're going to go to structural model creation standard. Defaults, use the default values here. Uh, Let me see. Under the abstraction tab, go and select the point mass or point inertia. You select this point. We're going to place the mass there, and it's going to be 2 kilograms. Good. You can see that there's a weight here. You can see that something that looks like a weight. Now, then we're going to create our spring. So we go to the connection, under the connections tab, see that, the connections tab, and go to the right, the third one from the left, there is a rigid connection and spring connection. We want spring connection. And notice that you can go between a point and the ground. And in fact, in the previous video segment, I did it all between this point and this point was used as the ground also. But here, I'm going to use as my first support this point. Okay, and instead of a ground, I'm going to select that point. So this is going to be there. And if you look close enough, you see that actually it looks like a spring. The actual shape, the distance is totally irrelevant, at least in my problem right now. Now, Uh, if you click on, see the stiffness is 4, stiffness of that spring is 4, and if you click on this no, on the enable advanced behavior, see that, enable advanced behavior, and click on the pencil to edit, notice that the value of the stiffness is already there. It says it's in X direction, but this probably is referring to local direction, so X is along the length of the beam, okay? Along the length of the spring, not the beam. Now, if you go and select the damping, nothing will happen except that you have to select the text. I suspect this is a bug that needs to be fixed, okay? Usually when you select on these boxes, this should light up, but it doesn't here. You select on the text there and you select FX because you have no other choice really. And the damping value is 1 Newton second, what is that? Newton second per meter. Okay, that's the unit of damping coefficient. Okay, very good. And we say close and okay. Now, we're done as far as the model structure model creation is concerned. Now, in most of my videos so far, I've been going to structural scenario creation, but there's some stuff here that you may not be able to find because this is not the entire, this is the stripped down version of the kind of Abacus program. So go down here, mechanical scenario creation, not structural scenario creation, mechanical scenario creation. And let's not use the general, because when you use general, there are some icons and some options will appear which has nothing to do with stress analysis. So let's do structural. And for the model, finite element model, select the one that you just created, which was basically mass and spring pretty much. Okay, now, in the previous video, I went to procedure and I selected frequency step without putting any restraint on the object. And it worked, there's no problem. I will do the same thing, but I'll show you that it's not going to run. Okay, so if you go to frequency step without putting any restraint here, 10 frequencies, but of course this is only a single degree of freedom, that's okay. And say all right, say okay, nothing else. And now we're going to go to simulate. Let's check the model. This is equivalent to the data check in the Abacus program. Work. Let's check the simulation check. Also will work here. There may be some warnings, whatever, but let's see. There were no issues when I did collapse everything to 1 point without any restraint. It gave me the correct natural frequency and the damp natural frequency once I did inserted the complex frequency step. But we'll run into problems here. Not at this stage, but when we try to run it, I'm pretty sure, or yeah, we'll find out. Actually, I'm not sure. Maybe here is okay. Yeah, that's okay. But when you try to run it by saying simulate, it will come back with an error, so it will not finish. Bear with me for a second. This is going to be very quick. There is a warning. Fine. Uh, Actually, there are no errors. However, look at the values that it gives me. Let's check the warning here first of all. Okay, so there's only 3 of them, no problem. But I really shouldn't have said error, but you can see that it gives me values, but these are not the stuff that these are basically there are no restraints, so this is the rigid body mode essentially. 3 rigid body modes because there are no restraints. Absolutely no restraint. So what I'm going to do is the following. What I'm going to do is I'm going to go back to that scenario. Okay, and I'm going to fix 1 point, just 1 point. Okay, so we go under the boundary condition, click on the fixed displacement at 1 point, and it really doesn't matter. Well, let's fix this. Okay, and well, we can do all three of them, or rotation or irrelevant here. So let's just fix. How about fixing in direction y? Okay, we can try the other ones. Okay, for example, let's try x. Let's try x and run it. Okay, see whether it works. All I do is the last one, just run. Now x is this direction, literally this direction. Let's see. I mean, obviously, if I had to do the problem, I would fix it in the direction x, y, and z. But, well, we just wanted to experiment and see what happens if we fix only motion in the x direction. We'll see. You see, it's no good because it still gives us essentially the same thing. So let's go ahead and this time properly restrain that in all three directions. So let's go to that restraint here, which I believe was in there. Double click. And let's try all three. The one that's concerning me is really direction Y, because this is vibrating up and down the Y axis, but let's run it and see what happens. I suspect you're going to get that natural frequency 0.225 hertz, and I'm pretty sure you will. There will be two rigid body modes too, which is basically motion in the, well, let's see, probably X and Z direction, but 0.225 is what I'm looking for, and we're going to be getting it. This is for the natural frequency, and then once this is working, then we're going to go and do the damped natural frequency. Yep, there we go. See? Let me close that. This is your 0.225 from the theory, right there. Now, to get the damped natural frequency, we're going to go back to scenario. There's a scenario and procedure. You see, now this is no longer dim. Once we did the frequency, this is a complex frequency step. You click on it and just say OK, and then simulate. You should be coming up with that damped natural frequency of 0.22 hertz. So the difference between this tutorial and the previous one is that previous one I couldn't see the spring, which is okay, there was no problem. I didn't have to put any restraints on it, it worked fine. But here if you create literally the spring, you do have to specify the uh, the restraints. Okay, the answer should be 0.22 hertz. Well, it's 0.225. That's not right. But look, that's because this is the frequency step. I want a complex frequency, not this one. This is step one. Complex frequency is right there, and there we are. One of them is a rigid body. The other one is 0.22 hertz, which confirms this number. Yeah, so that's pretty much it. I will be doing a few more video segments on this thing where I take the one with actually the spring and do an implicit dynamics, and then later on do a frequency response analysis.